Welcome everyone. Can you hear me now?
Yes, ma'am.
Okay, great. Thanks. Good. Okay, so a couple of quick announcements before we start. So there is a doodle poll for setting a new timing for the Wednesday lecture. So currently only a few people have filled it up, and we don't have a definite slot so far. So could everybody else please also fill it up if you haven't already? And if you are not part of the mailing list, please send an email to this particular address so that you can be on the mailing list. So if there are any changes or any slides to be shared or whatever, they will be done through this mailing list. So both of these things are in the chat. So please take advantage of that. Okay, so since we have a reasonable number of people, let us start. Okay, so the goal of today is to start with the introduction of gauge theories in order to understand the standard model. Okay, and the overall goal of the course is to understand what is the master equation that you would need for studying a realistic event at the LHC. So that equation looks something like this. So you have some cross section. I'll explain all of the terms soon. So the equation looks something like this. So you normally have a matrix element squared, which describes some sort of scattering interaction that happens in your collider. Okay. So this is what the matrix element squared gives. There is a phase space corresponding to this interaction. So that is the integration here. And usually, since we are dealing with the LHC, you have these particles themselves that come out of protons, right? So you have a probability distribution function for what kind of particle with a particular fraction of the proton energy will come out. So that is given by these functions here. So you sum over the fraction of momenta as well. So we will deal with this in detail later on when we talk about deep inelastic scattering. But this is in general what the equation looks like. And if you look at how to simulate this in a computer, what you normally see is this very complicated graphic that looks something like this. Okay? So you have, let's say, two protons. Okay? Then you have something coming out of each of them. Some sort of interaction that happens. Some particles that go out. So this is the hard process that we already have talked about. But this is not the end of the story. What you also have is you have some radiation that happens from all of these legs. That you need to deal with. And then we also know that you don't see any quarks or gluons freely in nature. So these things actually combine to form some kind of stable objects, which we call mesons or hadrons. So these are the things that you would see. So you see neither the particles that are coming out of the proton, so these things, you don't see the individual radiations, The only thing you see at the end is this sort of cluster of hadrons that come out at the end. So this is what your real process looks like. So when if you put a detector around your collision, then what you will see are the energy deposits and tracks that come from these hadrons alone. Okay. If you also produce some other particles like maybe photons or electrons or muons, you will see the corresponding signature with them as well. But the general point that I want to make is that this whole mathematical machinery that we've developed in quantum field theory to calculate this part here, which is the matrix element squared, really only gets us so far. So what is the job of Monte Carlo generators? They are called Monte Carlo generators. Is to essentially take you all the way from the collision, the hard scattering process, simulate all kinds of radiations, and then cluster whatever you have at the end into respectable looking hadrons. If those hadrons are unstable, then you decay them into stable final objects and so on. So all of this multi-step process is done by Monte Carlo generators. So that is going to be the goal of this course. Okay.
Excuse me.
Yes.
These green lines are gluons there.
These guys, yes.
Okay.
Yeah. Yeah. So in fact, I mean, they need not entirely be. You can also draw this picture for, say, an electron-positron collision machine at very high energy, in which case you will have initial state radiation in the form of photons. So you can consider this a fairly generic picture. The idea is simply that you have some charged particles here, and if you have charged particles that are being accelerated, then they're going to emit some radiation. So that's the main idea. Okay. Okay. So what we are going to do in this course is we are going to start as usual from the hard scattering part of the process. So we are going to understand the standard model very quickly. I mean, so this course is not going to be about understanding the standard model. I would refer you to quantum field theory courses or more dedicated theory courses for that. But having said that, we will go through the basic theoretical machinery to understand at least what is going on, because it is impossible to understand collider physics without understanding something of the basic theoretical machinery underneath. So that's the first part that we're going to do. Then we are going to study two things. First of all, how did we come up with the hypothesis of what is inside the proton? So what is the fraction of this thing coming out? For example, so this is something that we will study in deep inelastic scattering, and then how parton distribution functions are written and so on. And then we will talk about this probability of radiation and how to simulate these showers. So this initial and final state radiation, so these are initial states, these are final states. How initial and final state radiation is simulated is done by something called parton showers. Okay. So you will understand how those are simulated. We will talk about some more recent advances in Monte Carlo theory side, which allows us to make approximations of very high order calculations using some simplified methods, which are called matching methods. So you use simple quantum field theory diagrams to calculate the shapes of your distributions accurately without going to multiple loops or higher order effects in a consistent way. So we will talk about matching. Okay. And then finally, we will talk, not a lot, we'll talk a little bit about hadronization. And that is the process of turning what you have here as just quarks and gluons into hadrons. So sort of inverse of the process that you started with. So you picked out a particular parton out of a proton. Now you're going to do the reverse. You have some partons and you're going to make hadrons out of them. So this is essentially our goal. And then finally, what this course is going to do is apply all of this machinery that we have learned to some actual physics inferences. So we are going to study a little bit about electroweak precision tests, which is the study of the SU2 cross U1 sector of the Standard Model. So I'll tell you what SU2 cross U1 is in a minute. And we will also study in detail the recent data that is coming out of the Higgs and how you can interpret that using these kind of Monte Carlo machinery. Okay, so let's begin. Before we go ahead, so there have been some questions about last week's class. So, Rishabh, do you want to ask them now rather than waiting towards the end?
Anything is fine.
Okay. Yeah, you can ask them now. I think it's fine that we can deal with them right away.
Yeah. So first one was like with that formula, I think.
Yeah. Okay. So we'll come to the luminosity maybe a bit later. So I'll actually answer. I'll just read the questions that you had and then answer them right now. I think that's easier for me. So the first one that I wanted to address was about this dark matter experiment. So the question was, what is the assumption that goes in there? And it's the assumption that dark matter interacts with normal matter using Standard Model interactions. So there is an assumption that the dark matter does interact with ordinary matter, because if it didn't interact at all, then you couldn't detect it using this kind of a single target kind of experiment. However, the interaction does not have to be Standard Model. It can be a completely new interaction. The only requirement is that it interacts, and what we can detect is as long as the interaction is giving you a jiggling in the detector that is higher than the thermal noise. So you translate what that means for your theory. So if you have a new scalar particle that mediates the interaction, then you can translate what that means for the mass of the dark matter and mass of the scalar that mediates, and so on. So it doesn't have to be Standard Model, but it does have to interact in some way. Okay. The second question was to do with how do you know whether the incoming particles are fundamental or composite. So the Feynman diagram procedure actually doesn't make an assumption about whether the particle is composite or fundamental. So the modern way of thinking about this is in terms of what are called effective field theories. So you determine what your degrees of freedom are at the energy scale that you want to study. So suppose you want to study collisions between nuclei at low momentum, then we don't really care about what is inside the nucleus. We only care about the two nuclei as a whole. So in this case, your degrees of freedom are just the nuclei. You don't really care what is going on inside. Similarly, if you want to look at interactions that are very high energy, like we do at the LHC, then our degrees of freedom are really the quarks and the gluons that are inside the proton. So you don't actually care that the proton is composite. So your degrees of freedom are determined essentially by your energy scale, and it's sort of a recursive process. So you don't know beforehand whether these are indeed the right degrees of freedom. And what you would do then is you would devise sanity checks for your theory. Okay? So this is again something that we will talk about when we talk about deep inelastic scattering. If you have heard of any of these things before, what I'm talking about is scaling violation. So the first theory that was written down sort of predicted some sort of scale independence of all kinds of processes. So if you do the collision at one particular energy or another energy, you would get certain constant variables that should remain constant throughout these things. And what experiments found is that it does remain fairly flat for a long time. But eventually, when you go to very high energies, you find that there is a deviation from this constant number. And then that could be interpreted in terms of having extra gluons in the proton, for example. So rather than just the proton breaking up into parts, like you would think a billiard ball breaking up into 3 or 4 parts, or when we think of in our undergraduate days, a proton is made up of two up and one down. So instead of just proton breaking up into two up and one down, there is more stuff in there. And this is something that comes out from these kinds of extra measurements that you can perform. Okay. And the last freeze out question I don't fully understand. So could you explain what you meant by that?
So I basically wanted to know the process by which like this PP collisions actually produce like hadrons, because like from what I understand is in heavy ion collisions, there's an intermediate like coagulon matter, and that can like interact with each other and then freeze out to like produce partons, let's say. But
Right.
what happens in PP collisions?
Yeah, so this diagram essentially gives you the picture of what exactly we are talking about. So you can also get some indication of the parton soup-like thing from PP collisions. However, this is normally not what we do. That is not the picture that we use to understand these collisions. This partonic picture actually works much better than using the hydrodynamic picture that heavy ion collisions use.
Okay, thank you.
Okay. Good. Okay. Yeah, so there's another question about how to calculate the luminosity of circular colliders, but I'll come to it a little bit later. All right. So these were questions from last time. Does anybody else have more questions that they want to ask before we go to today's class? Just unmute yourself and ask if you have anything. Okay, excellent. All right. So so let me just start with a tiny bit of history. Because the story of the standard model is really not very simple. So in hindsight, we know all the components separately. But if you want to logically go through why we made certain hypothesis and why was a certain thing discovered the way it was, it's not a simple story. And so there's no simple answer. So I'm just going to try and disentangle it a little bit. Okay? So the story starts about somewhere in the 1950s after the World War. So there was, as you can imagine, a lot of interest in understanding nuclear physics and subnuclear physics. So there was a lot of money that was given to scientists to build lots of accelerators. And as soon as these accelerators were turned on and collision started, they found a lot of new particles being produced. Okay? And they came with all different kinds of charges and all different kinds of masses. And nobody really had a clue as to where they fit in properly, because up to that point, we had atoms that were made out of protons and neutrons, and you had electrons orbiting them, and we had great success in calculating what is it called? The spectra of different kinds of atoms, very accurate measurements that we had. And then for the atomic bomb research, people had some models of nuclear physics. People understood how radioactivity worked to a point. And so this whole new burst of particles that came out, they were all called mesons because they had masses between the proton mass and the electron mass. So they were sort of somewhere in the middle. They had all different kinds of charges. Some were charged, some were neutral. Nobody knew where to place them. There was also a decent amount of improvement in weather technology, meteorological technology, and people could send up high altitude balloons. And people started experimenting and looking for new particles also in the upper atmosphere. And they found similar kind of particles of this middle mass between proton and electron also in the upper atmosphere. So we had this whole range of mesons and nobody fully understood what was going on. So a lot of things sort of happened all at the same time. So firstly, there were some theories written down to understand radioactive beta decay. So we had the Fermi theory for that, which sort of seemed to postulate that since you have a finite lifetime for radioactive beta decay, there must be some kind of force, which they call the weak nuclear force, which breaks apart the nuclei, turns neutrons into protons. And because it has a finite lifetime, it must be, I mean, it's probably just a small distance force. And now we think of it as something that is being carried by a mediator that has mass. Okay, so that's how we understand it now. The second obvious question to ask is, the nucleus has a lot of protons, and we know that like charges repel in electrostatics, right? So how is it possible that these two protons can be held together very, very close without breaking the nucleus apart? So then the hypothesis is obviously that you need some sort of strong nuclear force that holds it together, but this should be different from the force that causes beta decay, because beta decay is a force that sort of disintegrates the nucleus and not really keeps it together. So you have this other strong nuclear force that we also don't understand. So there were theories. For example, there was this Yukawa meson theory that was proposed, which turned out to be not the right one, so we don't study it so much anymore. But there were lots of things going on at the same time. And one of the nice ideas that Gell-Mann came up with was the idea of using symmetry structures, or a mathematical concept of groups, to group together the mesons that were coming out of all of these experiments into certain patterns. So what he did was he assumed that there was some other fundamental particle, which he called quark, and all of the mesons and hadrons were actually composites of these quarks, and then he could fit them all in nice kind of patterns. So all of this seemed to be very confusing, and you should know that the original model that was proposed by Gell-Mann is also not correct. So what we have now is actually sort of a modified thing, but the idea is absolutely stands. Okay, so that's so here is the idea that we have now, okay, that we deal with now. So this is with the force of hindsight. Now we know what the theory looks like, so it's going to be much simpler looking back. Okay, so we basically have matter, which is fermionic and spin half. And you have forces which are carried by particles that are bosonic. So they are spin 1 mostly. So we'll deal with the Higgs later. Okay, so right now let's just stick with this. Okay. And the heuristic idea is something like this. So you can think of this very simple picture where I draw space horizontally and time vertically. Any particle interaction can be thought of as something like this. So you have some matter particle that then emits some kind of force particle here and gets deflected. And then that force particle is absorbed by some other particle and it too gets deflected. So this is essentially just, you can think of it as repulsion between two electrons. So that's the microscopic picture we have of how we understand these interactions now. Okay? So to understand it further, we are going to just revise some of the formalism that you might already know. So we're just going to talk about the Dirac equation first. Okay. So the Dirac equation is an equation that describes fermions. And normally you have a force spinner that is traditionally given the name psi. And you can think of it as two spinners that are left and right-handed. So this is essentially a 4-component object. The top two are thought of as left-handed, the bottom two are thought of as right-handed. And you have these gamma matrices that are used in the Dirac equation, and one particular extra gamma matrix, gamma 5, which looks like this. So this is the most commonly used representation of the gamma matrices, where you have this sorry, this should have been minus. This looks like this, and then you can sort of project out the left and right-handed components by using this projection operators. Where PL is defined as 2. Right, so this is the most common notation that is used in particle physics. And the gamma mu's themselves are also sort of block matrix objects that look like this. And sigma mu looks like, the first one is just unity, and the second, third, and fourth components are the polysigma matrices. Right? So you have sigma, sigma bar is simply 1 and minus sigma. Okay? So this is what it looks like. And then you have the Dirac equation that is given as right. So this is the well-known Dirac equation. And you can, in fact, derive this from this particular Lagrangian if you want. Okay. So you can yes, motion. Okay. So is there anyone here who has not come across this at all before? Okay, good. That's good. So, all right. So then we introduce the first fundamental idea for the standard model, and that is the idea of a symmetry. Okay? So symmetry is a transformation that leaves the Lagrangian invariant. Okay? So if you remember the path integral formulation, what you have is that you have an amplitude that is given by an integral where you have the action exponentiated, which gives you the amplitude corresponding to each path that is taken by your particle, and then you have certain, you would just integrate over whatever fields you have in your theory, right? So if you've looked at this before, so you know that there is this kind of an amplitude term, which essentially gives you the probability of a particle following a particular path, which is given by this action integral, right? And the action integral S is always given by d for x, right? Where L is the Lagrangian density. So basically what the symmetry is, in some sense, you can think of it heuristically, what the symmetry is basically telling you is that whether it takes one path or the other, there is no difference in the probability. So that's the heuristic understanding of what this symmetry is telling you. And mathematically, what you simply want is you want to find a transformation of your Lagrangian which does not change the form of the Lagrangian. Okay? So one particular symmetry of that you can think of for this would be your psi going to e to the I alpha times psi. And you can just check. So I will leave this for you to do. You can see that if you put psi goes to e to the I alpha psi, psi bar would go to e to the minus I alpha psi. Right now, psi is independent, it's just a constant. So basically it just goes through this del mu and you have the Lagrangian staying invariant. Okay? So this is an example of what is called a global symmetry. And the name global is sort of retrospective, because there is something called a local symmetry, which we will learn about in just a second. But what it usually just means is that the parameters of symmetry that you have do not depend on space-time. So it's just a constant number. So that's usually how you can understand global symmetries. So this is one example of a global symmetry. And if you recall the Noether theorem, this tells you that there is a conserved current corresponding to every global symmetry, right? And that current is given, this is the formula. So you had psi going to e to the alpha psi, which is just approximated for small alpha. So if you write this as psi plus del psi, that tells you del psi is nothing but I alpha psi. Okay? And you can calculate what this quantity here is, looking at the Dirac-Lagrangian, and you would just get so which tells you that G mu simply psi is alpha is the parameter. So this is your conserved current. Okay, so yeah, I'm sure all of you have recognized this quantity right away also. Okay. So so this is something that you might have studied before and come across before, but I would just want to ask you, do you know what this symmetry essentially corresponds to? So what is exactly happening here? So do we have any guesses?
Q1 symmetry.
Yes, what does that mean?
It's just a phase like e per I alpha. That is one dimension unitary thing, right?
Okay. No, you're using all the right words. I just I mean, you're not saying anything wrong. I just wanted to go a little bit deeper about what is happening. Okay. So what you can think of is happening here is that there is an internal coordinate that is sort of being rotated. So you can think of it as a phase. So this is just for completeness. So normally, if you're looking at a complex plane, you have some z to start with, and e to the I alpha times z1 takes you to some number z2, right? So this is just what this rotation is. Okay, so z1 had some phase to start with called, say, theta1, which was some r e to the theta1, and this guy now has r e theta1 plus alpha. Right? So this is what you have. So you can think of your field having this internal degree of freedom that you are rotating when you rotate this extra, by applying this kind of extra phase. The reason I'm insisting on calling it an internal degree of freedom is that you can actually have fields that have multi-dimensional internal degrees of freedom. And in that case, you are not just rotating by a single phase that is a number, but by a matrix. So you have to think of it as having an internal degree of freedom that is being rotated by this extra symmetry. Okay? So if you want to have this symmetry and you know that this is your Lagrangian, and since you've just done this very simple exercise of showing that it's invariant, it must be obvious to most of you that the thing that will be invariant is anything that sort of keeps psi bar psi invariant is going to keep your Lagrangian invariant as well. So if you have psi going to e to the I something and psi bar going to e to the minus I something, then this is a good transformation. Okay? So you can just also write it as psi going to u psi and say psi bar goes to. So remember, psi bar is psi dagger gamma 0. So this would be u dagger gamma 0, right? And the gamma 0 will commute with this u because they have different dimensions. So you can just take it in here. That's just psi bar. Okay. So anything that leaves psi bar psi invariant simply means you need u dagger u to be 1. And we know these kinds of transformations, they are called unitary transformations. Right? So any unitary transformation will work. So you can have n number of degrees of freedom internally. As long as the transformation is unitary, you are fine. Okay? Okay. So then you would ask the question, how would you even go on determining how many internal degrees of freedom you have? Because if anything works, I can put n to be 2000. What is stopping me? So how do you know whether a particle actually has an internal degree of freedom or not? Does anyone have any ideas about how this can be done? Okay, so there is no one answer fits all answer to give you, but I will give you a particular case of what we do for quarks. Okay, so we haven't talked about quarks yet, but I'm sure you've all heard the word before. So quarks are certain particles that you can think of as fermions that have 3 internal degrees of freedom. Okay, so this is a particular case. Okay, and these internal degrees of freedom we normally refer to as color. Even though they have nothing to do with actual physical color, they're just called color. Okay, and the way you count this number 3 is what you do is you may build a collider out of E plus E minus and let it go into quarks. Okay, you count how many of this kind you have, and you take the ratio of E plus E minus going to some other known particle, which in this case is the muon. Okay. So you take the ratio of this. I'm just going to write n, which is just the number. Okay. And if you are at high enough energies, then you would expect that this number essentially should just cancel. So if you have one species of quark and you just have one species of muons, then this number essentially is just gives you the charge of the quark. So it might look a bit charge. Okay. So it's just the ratios. Muon has the same charge as the electron, so it's just 1. That's why there is just 1 in the denominator. So it's proportional to the charge of the particle that you produce. Okay, so this you would expect to just be the charge of the quark. However, what you actually find in the answer is that this number is 3. So this number is actually 3 times what you would expect. And then you can sort of claim that this is because you're producing 3 kinds of internally charged objects. So you're producing 3 times as much because you always sum over all possible final states, right? So just like you produce sum over all spins in the final state, when you calculate your matrix element, you will also sum over all colors. And when you do that, you will get this extra number. Okay, so that is one answer that I can give you about how to count internal degrees of freedom. Okay, so any questions up to here? So now we talked,
Ma'am,
yeah.
the path integral should be e per is. Previously, I've written that.
Yes.
Yeah, e per plus is.
Okay. Sure. Okay.
Ma'am, by charge, do you refer to color charge or normal electrical charge?
So here I'm referring to the electric charge because the diagram that you have is actually mediated by the photon. So this is what the diagram looks like. So
Okay.
we'll come to this again in detail when we learn about QCD. So you don't have to remember any of this, but I just thought that this would be the natural question that would come into anyone's mind, is that if everything is allowed, then what determines what should the number of the SUN be? So that's why this was sort of a preemptive answer given beforehand. So we will come to this in detail soon. Okay. So we talked about this symmetry here, where your alpha was a constant number. Okay? However, what happens if your alpha is not a constant number but depends on x? So this might sound a bit funny because the earlier example where we looked at the global symmetry was, you can also think of in the sense of change of coordinate system, right? A kind of global symmetry is changing of a coordinate system. So we know that our universe is isotropic, or even if we're, let's deal in the classical sense, just Newtonian mechanics. We know things should be isotropic in 3 dimensions, which simply means that your system is rotationally invariant, right? So that's one way of thinking about it. It just means that if you change your coordinate system, you should not see a change in the physical phenomena that are happening. So this is sort of a weird kind of transformation, and this is called a local symmetry or transformation. Okay. And you will notice right away that your Lagrangian, which looked like is not really invariant anymore. The mass term is fine. However, this term actually has 2 components. So you will have okay, so psi bar gets an e to the minus I alpha, psi gets an e to the plus I alpha, and then there is a del mu. And what the del mu does is that you have 2 terms now. One term that just looks like psi bar, term is psi, and you have a term that looks like psi bar. Right? So you have these 2 terms, and in particular, you have this one extra term here. Okay? And you will recognize this psi bar gamma mu psi essentially looks exactly like the current that we had derived earlier. Okay? So to get rid of this extra term, what you can do is you can add another field. okay, which I'm going to call A mu. So you remember this this term that we have here is a vector-like term. So if you've studied the Dirac equation, you'll remember that this transforms as a vector. Okay, so basically you want to have a term that cancels this exactly. So that's why you start with another vector field, which I call here A mu, just out of tradition. And the A mu field transforms in this way. Okay. So every time psi goes to e to the I alpha psi, A mu goes to A mu plus d mu alpha. Okay. And then to your Lagrangian, you will add this extra term. Okay. Oh, did I not write this correctly? Yeah, I made a mistake up here. Can someone point it out? So there's a del mu in here, right? The del mu acts on e to the I alpha. So there should be a del mu alpha. Yeah, exactly. All right, good. So now you see that by adding this extra term, and you want to subtract this out, right? So this you will add it with a minus sign. Okay. So that means your Lagrangian now looks something like this. Let's make it here. Okay. So your Lagrangian looks like this, and in particular, you can write this here. You can define a d mu. That looks like d mu. Okay. And then your Lagrangian looks like. So I'm ignoring the mass term. Okay. So let's say m is 0 for now. Okay, so let's ignore the mass term for now. So this is what your Lagrangian now looks like. And again, I will leave you to check. And this is invariant. Okay, so this is your transformation now together, and this Lagrangian is now invariant under it. Okay. So this guy d mu is what is called the covariant derivative. Okay. And the meaning of covariant is it transforms in the same way as the original field. So if psi goes as e to the I alpha psi, then d mu psi also goes as e to the I alpha psi. Okay.
Ma'am?
Yeah.
Hello?
Yeah.
If we had the mass term also m psi by psi, then also it would be invariant.
It's still invariant, yes. I just don't want to deal with it right now. That's why I put it to 0. But yes, you're right.
Okay.
So it's not, I'm not putting it to 0 because it's a problematic term. I'm just putting it to 0 because it's not super important for us right now. And eventually we will see that the standard model mass terms are written not in this very simple psi bar psi kind of notation, but a more complicated interaction term with the Higgs field. So it's not going to be very important for us later on as well.
Yes,
So,
okay, fine. Yeah.
so that's why we just kind of ignore it for now. Okay. So, so what I showed you here is sort of a trick of making a global symmetry a local symmetry. So you started with a global symmetry, and if you want to make it local, then you need to add an extra vector field that absorbs whatever changes to the Lagrangian that your localization is making, is causing. Okay? And what does this extra term that you added, so this is the extra term that you added, what does that mean? Is that you have a psi bar, psi, a mu kind of term, which sort of looks like this, right? Psi bar, psi. So it essentially gives you a new vertex between your original fermions and this new X vector particle, which is bosonic, it's spin 1. And you can think of it as a photon. So if your psi's are electrons, then the a mu is a photon. So what we've just written down is a description of electromagnetism. Okay? So now if you have multiple particles, they can each have a different charge. Okay, so what do I mean by that? Different charge. So one thing you can do is you can have different particle fields, and then you can add a different a mu for each particle to absorb exactly its own alpha. Or you can have the same a mu, and the way it couples to each of these particles. So this you can think of as the coupling of this a mu to the particle. And the way we've done it here is essentially it absorbs exactly the alpha that corresponds to that particular particle. But what you can instead have is you can have each particle have its own charge. Okay? And then the coupling of each particle to a mu will also have the same charge. Okay? So this is the same Q. And in that way, you don't have to add a different a mu for each different particle, but you just have different charges corresponding to all different particles. So this is the mathematical representation of what we think as electric charge. So for electrons, this Q would be 1. If you have something that has 4 times the charge of an electron, like the alpha particle, this Q would be 4, and so on. Okay. All right, so this. Okay, excellent. All right, so any questions here up to here? Okay. So then again, I want to turn to understanding intuitively what it would mean if you have not just the single phase internal degree of freedom, but a matrix valued, or rather, a matrix valued transformation. So you have an SUN transformation. Okay. So for that, I find it useful to think of in terms of matrices. So your normal Dirac equation you can think of as something like this, right? Where this guy is your gamma mu, and this guy is your psi with 4 components, right? And then this is 0. We're working in the massless case, so this is just 0. So this is what it looks like. So when you add an extra degree of freedom, what you're essentially doing is, instead of just having these 4 numbers, what you now have is essentially this extra internal space. So you can think of it like this. So let's do for an example, the simplest case where you have SU2 instead of just U1. Okay, so that this is the next unitary group. And then let's call our internal degrees of freedom up and down, U and D. So remember our normal Dirac fermion has psi L and psi R, right? This is not what I'm talking about. The psi L and psi R are here. Okay, so this is an internal degree of freedom that you can think of as a hidden dimension inside. And then what you have is you have your normal gamma matrix that acts on this direction, but you can also have transformations that act in this direction. So basically they will take this U and D to some other combination of U and D. So that is what this SU2 does. And this is your normal variance. Okay. So this is how they act. And in fact, it is a fundamental theorem that we have, which you might have heard the name of. It's called the Kolben-Mandula theorem, which says that if you want your scattering matrix, the S matrix, to have certain nice properties, like it preserves probabilities and so on, then you cannot mix these two. So you cannot have an internal transformation that changes the space-time properties of the particle, and you cannot have a space-time transformation that changes the internal properties of a particle. So for example, you cannot change the charge of a particle by performing a space-time transformation. Okay. Okay. So this is to understand a bit more about how to visualize these objects. Okay. So let's now, instead of our small psi, let us write a capital Psi that looks like this. Okay. So now what I'm doing is I'm essentially not spelling out the vertical side, and I'm just focusing on this side. Okay. So I'm not going to spell out all the indices of the spinor side. Okay. And the internal transformation then looks like your psi goes to e to the I, A psi, where these TAs are generators of the algebra of the internal symmetry.
So there are 4 copies of psi u and psi d, right?
Yes, I mean, not copies essentially. It's there's one what is the word? Spinor, 1,4 spinor for psi u and 1,4 spinor for psi d.
Okay.
Right. So there's in here. So both psi u and psi d have their own Dirac equation.
Okay. Okay.
Yeah. All right. So this is just writing the same transformation, except now you have instead of just alpha a, which was just a number, now you have this alpha a. Alpha a's are still numbers, but they're multiplying each of these matrices. So I will tell you in a minute what do I mean by generators of the algebra. So I just want to do this very simple exercise of rotation in the xy plane. Okay. So you had this particular vector to start with, and you want to rotate it by theta, right? And we know what this looks like. So x prime y prime looks simply like cos theta, sin theta, sin theta, cos theta of x and y, right? If we want to write this in terms of the exponential notation that we wanted to write, so let me call this guy r. Okay. The way you do it is the following. So you can just take this as a recipe. take the derivative of r with respect to its parameter, setting parameter to 0. Okay, so this gives you 0, 1, minus 1, 0. And if you look at exponent, let me call this guy sigma. Okay? And if you look at exponent of theta sigma, you know the first term is going to be 1. The second term is going to be the sigma, which is, sigma times theta, which is going to be 0, theta minus theta 0, which you notice right away is the first term in the Taylor expansion of sine theta. And similarly, minus theta is the first term in the expansion of minus sine theta. Then you have theta squared by 2, 0, 0, theta squared by 2, and so on. So this is essentially a way of exponentiating. So you're finding this generator. So this guy is called the generator. Okay? And this is how you find it. Now, as physicists, we don't really like these kinds of matrices because these are anti-Hermitian. So you notice if you take the Hermitian conjugate of this, it's a real numbered matrix, but if you take the transpose, then the minus jumps from down, up, down here to up here. So it's essentially an anti-Hermitian matrix. So we like Hermitian matrices. Because they tend to give real valued eigenvalues. So we tend to write it like this: I theta sigma 2, where sigma 2 is our normal polymatrix. Okay, so you could have written down this same transformation as x prime is e to the I sigma 2 theta x. Okay. So this is what we are going to do also for, so this is essentially what we're doing here as well. So your TA in this case are SU2 generators, which are, again, as we know, the polymatrices. So sigma by 2, there are 3. So A goes 1, 2, and 3. So you have 3 parameters, 3 alpha A's, each of them multiplying a different polymatrix. So this is what the transformation would look like for SU2. Okay, so let's write it back into our Dirac equation. Okay. So you had L psi bar by del psi. Okay. So that's psi bar minus okay, so one more thing changes, which we should have also talked about. Okay, so remember A mu goes as A mu minus del plus del mu alpha, right? So since you have 3 alphas, you also need 3 A's. Okay? So you have these 3 A's as well. Maybe I'll come to that in a minute. It might be easier to just look at what happens to del mu psi. Okay? Goes to del mu. So you have this extra TA term that comes out, and that is going to multiply this extra internal degree of freedom of the psi. Okay? So when you have, earlier you had psi bar gamma mu psi, now you have a term that looks like psi bar gamma mu TA psi. Okay, so again you can look at this diagrammatically. So you had psi bar gamma mu psi, right, where you just had one direction or one dimension, but now you also have an internal degree of freedom to contend with. So if this guy is taking care of your spinor indices, then you also have psi I, which are the SU2 indices now. G, psi G, which is multiplying all the spinor indices. So that's, you can think of as then having an extra component here, an extra component here. And then there is an extra matrix that multiplies here. Sorry for the bad drawing. All right. Okay, so you have this term here. And your interaction term would then look like psi bar gamma mu TA psi A mu A. Right? So this is your interaction term. So you can think of this in another way. You can actually put these guys together. So do the multiplication beforehand. So you know that this A is going to get multiplied and summed over. So what does TA A mu A look like? So this looks like essentially sigma 1 times A mu 1 plus sigma 2 3. Okay. So that looks like simply like this. Okay. So you have a matrix, so you can also write this simply as A mu, like our old notation, and then you would have psi bar gamma mu A mu psi. I'm keeping it in the middle because it still has a matrix valued multiplication to both psi and psi bar. So remember that there is this extra multiplication going on. So you don't want to bring it outside and just have psi bar gamma mu psi. So you still write it like this, but it looks similar to the simple one-dimensional case that we have, where your A mu now is this matrix valued of this matrix valued form. Okay. So this I would suggest that you get familiar with this sort of notation because it makes a lot of things very simple. And so what I'm going to do now is I'm going to do a toy model with the example that we've written just now to illustrate what is possible. Okay, so you have this kind of an A mu term, and let us look at what kind of terms you get. So you had psi u and psi d. Remember, that was how we wrote our psi. And then you have this A3 by 2. 1. So I'm going to suppress the mu as well right now. It's not super critical. So I'm just doing the the internal degree of freedom multiplication right now. I'm not doing the Lorentz part, so that's the mu's. Okay. So A1 minus I2 2 minus I2 minus A3. Okay. And then you have psi u, psi u. Okay. So what does this give you? There's a bar here, sorry. So you have psi u bar. So there's a gamma mu here, remember? Gamma mu A3 by 2 psi u plus psi bar u A1 minus I2 by 2 4 psi d. So these guys all have mu's. Okay. So you have these 4 terms. Okay. And you can redefine by W A1 u minus plus which is what I'm going to call my W. Okay. So let me just call this term I for interaction term. Okay. So your I now looks like so does everybody agree that we'll get something like this? So you have 2 terms that take u to d and d to u, and these 2 terms essentially that are between the same kind of fermion. So you still have u and dd. Okay. So what kind of use would this model be of? Okay. So what use would these be of? So remember, it's a toy model, so it's not really physical, and we'll come to why it's not physical. But assume, for example, you have 2 species. One of them is given by, let me just get the charges right. So there's a psi n that you write like this, and a psi l that you write like this. Okay. Then what you could do is you could think of describing beta decay. So this is your proton, this is your neutron, this is your electron, this is your neutrino. You could think of it as being described by this particular diagram. Okay. So you have a neutron that couples to a proton. In the same way, you have this up-down kind of interaction. And similarly, on the other side, you have an interaction with the electron and the neutrino. Okay. So you could potentially say that this describes your beta decays completely. However, this theory, you will notice, has another particle in there, which is the A, right? So then what can this A be? So you say, oh, but we also need the photon. So maybe the A is the photon. And at first glance, it seems fine. However, you will notice that this particle A3 that you have left over has couplings both to up and down type here, right? So which means that it will couple to both the proton and the neutron and also to the neutrino and the electron. Whereas in real life, we know that the neutron and the neutrino is chargeless, which means that the photon doesn't couple to it. Okay? So it doesn't work because N and nu couple to it. So in the language of our charges that we had earlier, what we have is this U comes with as well. U comes with a charge of plus half and D comes with a charge of minus half, right? And you could actually artificially just add a extra charge in there, which would be a factor 2. So then you could have U of charge plus 1 and D of charge minus 1. The thing to remember is that they are always proportional. So that one is plus and the other one is minus of the same number. So there would not have been a way to have chargeless neutrons and chargeless neutrinos, which is why this simple model doesn't work. And we need to go to a more complicated theory to describe a realistic beta decay and to get both the electromagnetic side with the photon and the beta decay together. But another thing that this illustrates is that a single theory can give you more than one force carrier. So you have a charged carrier that I call the W, which mediates the beta decay, and a neutral particle, a neutral charge carrier as well. So that's again another feature to keep in mind. So I know that this can be quite a lot if you're seeing this for the first time. So I would suggest that we go kind of slow and go through this again and again till we become familiar with this kind of notation. Okay. So just to recap, what we are doing is we started with this simple picture of a one-dimensional transformation. Okay. So everybody understood that this was just a phase transformation. And if you want to make the phase local, then you can do it by coupling an external vector field that you call this A mu. And it has this nice property that it transforms in a particular way, that it absorbs the extra terms that you get from this transformation of the fermions. So that's how you define the covariant derivative. And you can write the Lagrangian in this nice form, and it gives you an extra interaction term that describes this piece of interaction between the fermions and this extra gauge boson that you define. Okay. Then we talked about charges, which means that you can have multiple fermions at the same time with the same gauge boson, and just the interaction term corresponding to each of them will be different. Or similarly, you can say that the covariant derivative corresponding to each of them will be different because it will carry its own charge in each of the covariant derivatives. So then we said, okay, let's not just talk about simple numeric phases, but you want to talk about transformations in multi-dimensional internal spaces. So we had this simple picture. The simplest case was SU2. And so we just rewrote the whole transformation, e raised to I alpha psi, in a language that allows us to deal with these internal symmetries in the same way. Okay? So we defined something called the generators of a symmetry. So as an illustration, we looked at this generator of SO2. So that if you want the official, or rather the mathematical name of this group, it's SO2. So we looked at how to calculate the generator of this simple symmetry. And then we didn't actually calculate it, but since we looked at SU2 for so long in quantum mechanics and so on, so we just said that the generators of SU2 are the Pauli matrices, and we didn't derive them. But given that, we found essentially what the conserved current is. Okay, so that looks like this. It's the conserved current. Should have it here. And we asked what our interaction term now looks like. So the interaction term is of this form, and you can sort of condense the generators and the gauge bosons that you have into this matrix valued form, which makes it easier to understand. And then we wrote down this toy model with SU2 that gave us a model of describing the beta decays, but it's not a very good model because it has all these problems. Okay, so that's a quick summary of what we did today. So do you have questions? Do you want me to repeat something?
Ma'am, in the previous slide, can you
Yeah.
Yeah. So the last term should be W mu minus, right?
Yes, absolutely. Yes, so I'm while writing, I tend to make mistakes. So please keep me on my toes by noticing all these small mistakes that I make.
Also, the definition should be I there.
Yes, absolutely. Exactly. So these are the terms that we are redefining. Okay, so you had A1 minus IA2. Great, thank you. All right. Okay, so we are going to stop here for today, and we'll pick up and write a more realistic theory next time.
So when is the next class? Is it?
Yeah, so I will send an email about when the next class is. So since you guys are here, it seems from the doodle so far that Wednesdays and Thursdays, or rather any of the afternoons, Wednesday, Thursday, Friday, none of them seem to be suitable for everybody. So I noticed in the timetable there is just open it again. There is an open slot at 12 o'clock on Fridays. Is that okay with everybody? So maybe I'll just ask now, maybe just use your yes, no buttons. So I see there is no, TIFR at least has no official lecture on Friday at 12 o'clock. So is that okay with everybody?
We have the QFT2 starting from
2 o'clock.
2 o'clock, and also before that we have up to 11:30 the SSP solid state physics class.
Yeah, exactly. So so 11:30 you have that, and then 12 o'clock you have nothing. Nobody has anything. That seems to be an open slot. So if that is okay with everybody,
I would also like to join that journal club, electric journal.
Oh yeah, we have the journal club at that time. That's why it was open. Yes.
Ma'am, if anyone does not have any problem, maybe the QFT can be shifted from to the 5 to 7 slot, because
Yeah,
I don't think anyone crediting QFT2 will be crediting the QM2 and the statistical physics 1 courses.
yeah, but we cannot shift other professors' classes, no? They might have other conflicts that we don't know about. I cannot guarantee that Gautam is going to be free at that time. So since he chose this time, he must have had something else in mind, right?
Yes. Maybe they can like ask and then we can decide. Or yeah.
Yeah, that's a possibility, but yeah, okay. Let me first